Thank you for attending this talk. I will speak about co-regulated timing in music or dance ensembles, and I will do that from the perspective of listening. And I will present an analysis tool based on Bayesian statistics. So the concept is related to co-regulated timing, which involves a coordination of actions by musicians or dancers in time, and so due to this coordination, the ensemble creates a particular tempo of different duration objects. And our assumption is that in view of this co-regulation, humans that participate in the ensemble, they predict the timing of the ensemble in terms of a constancy. They assume that the timing is somehow constant despite the different fluctuations that occur. So we approach this from the viewpoint of discrete onsets, and we also have different objects which we call onset intervals. And typically in music, you have different types of such objects. Let's say an object with fluctuations around 200 milliseconds, another one 400 milliseconds, and another one 800 milliseconds. The idea is then that when I perceive an onset earlier than my expected constancy, I adapt my onset in view of that constancy assumption. And we will handle that in terms of Bayesian inferencing about meter and rhythm. We can also see it from the viewpoint of a so-called Kalman filter, where we track those different objects over time. Despite fluctuations, we track it and we obtain a trajectory that is our prediction about the next onset object. This also adheres the theory of predictive coding. Let's give a concrete example. These are artificial stimuli. This is the time in samples. 100 samples is 1 second, so this is 20 seconds. The vertical axis is the duration of an inter-onset interval expressed in log dur. That means in milliseconds, this is about 256 milliseconds. And we see that the production of the onsets, first of all, they go slower, and then here they go faster. The duration becomes smaller. And so the data are the same in the three graphs. And basically what the Kalman filter does is it draws a line through these data points, and it tries to capture as much of its fluctuation, where it tries to capture the mean over those onsets over time. So if we compare the three trackings, then we would say that maybe the middle one is the best one. Here we have overshooting. Our model is too dynamic, so to speak, and here our model is too rigid. And here we show the diagnostics of this analysis. So we calculate the distance of every dot to the line. And now the prediction line is here, the horizontal line, also here, of this line. And this one is of this very dynamic line. And here we calculate the distribution. And we see that it is a normal distribution, but we also have to consider how it evolves over time. This one is very structured, and actually we want a more unstructured distribution over time. So this is what smoothing is about. The Bayesian inference is basically a smoothing of the timing objects that are perceived. And so these timing objects, they are the what we call inter-onset observation. The inter-onset class is the constancy in those observations. And the meter is what can constrain the relationship between different classes. So for example, if we have classes, one class about 200 milliseconds, another one about 400 milliseconds, and another one 800 milliseconds, then we can, over time, we can keep the ratio constant. And so this is a hyperparameter that constrains our tracking, so to speak. And based on the results, we can do an analysis of the distributions that we obtain. So fluctuation one it is called, is the prediction error calculated as the mean of the absolute values. Fluctuation 2 is the standard deviation in that distribution. And stability is then the drift over time of the predictions of the IOI classes. Here then we see a major feature of our approach is regularization. And here we see an example on a data set. This the same on the left and the right one. We see here a drift of onset values up and down, and this one remains horizontal. So if we don't constrain the ratio among the predictions, then we see that the predictions just follow the classes, follow the mean of the observed onsets. But if we do constrain these predictions, we end up with the same ratio among prediction values over time, but we see that our prediction error will typically increase because we don't capture their mean, actually, because we are constrained by the meter. And the black dots that you see here, the small black dots, they represent the tempo, which is a linear combination of the three values of the IOI class over time. Here we see another example, the choir. In this case, we use 4 microphones, and we do the onset extraction for each signal of each microphone, and then we mix all the onsets. We see that due to asynchrony among the singers, we have a lot of very small intervals, which we try to neglect. So we consider them as outliers due to the fact that the tracking is within a certain scope. But here you see that if the tracking is not constrained, it can suddenly shift to the smaller intervals, and then it follows those small intervals. Typically, we don't want this. When we impose the meter as a hyper prior or a hyper parameter that constrains the variability of the trackers, then we see that the trackers can nicely follow the onsets. And in the lower panel, we see the same. So no regularization to the right here, but now the input is from one single microphone that did a recording of the entire choir, and we select the onsets in a proper way, in the sense that if they are too close to each other, we already select them, so we don't have any outliers in this case. But you also see that the regularization is the best solution. In this example, we see rocket singing. So also here the timing is correlated, and in this example we see another group.
Bum 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 bum.
Both groups are very different in timing outcomes. They have different tempi. The data are not stationary. That means that the tempo is fluctuating. But here we see the tracking of the first ensemble, and here the tracking of the second ensemble. The second ensemble also had a lot of misses and outliers. And so the task is to draw 3 lines through these data points, which is not always easy. When we impose the meter on top of it, we see this result. And here we see the global measures of the distributions obtained through this analysis. I don't go into the details of the tracking mechanism, which is a Bayesian approach where we predict an observation, we get an observation, and based on the prediction error, we adapt our prediction unit. We do that every sample. So we do that 100 times a second. or maybe 1,000 times a second, depending on our sampling rate. We work on discrete times, which is perhaps a limitation because first we have to do onset detection, either manually or with annotation, feature extraction algorithms. This is a limitation. The second limitation is the priors. We have to set them in a proper way, otherwise the result can be very strange. But in any case, the BListener algorithm, how it is called, is suited for real-time implementations and it could be used as a perception module in an artificial musician that participates into a co-regulation task. This software is available at GitHub, and this is a reference for my talk. Thank you very much for attending.